Yes, we'll continue with the stress concentration chapter. So this is the next part in that, methods of reducing stress concentration. Okay. So in the previous lecture we have seen what is stress concentration. So stress concentration is nothing but wherever the discontinuities, like a plate with a hole or plate with a notch or plate with a groove, or if there is a sudden change in a cross section, then the stress is concentrated more in that region, right? So also we have seen a practical example of a plate with a hole. I have also shown you a color image in that. Wherever the hole is there, so there the stress is concentrated more. So we also took one small example and we also proved that. So reason is the cross-sectional area is minimum near the hole region. So also proved that, and also you have seen that color patterns of stress variation at the end. So that is the proof. And also sudden change in cross-section. So that example also we have seen at the end of previous lecture. So I hope it is clear. So apart from stress concentration, you have also seen stress concentration factor. So what is that? So that also we have seen. And what are the methods to find stress concentration factor? So those things you have seen in previous classes, and those who missed, the link has been shared, so you can go through it once again. Okay. So coming to today's lecture, methods of reducing stress concentration. So first method is drilling additional holes. Now you see here in the first model which I am showing here, there is a plate with a hole, and these are the hypothetical lines. These lines will not exist actually, but to understand the stress patterns, stress variations, so you can observe these lines. Okay. So wherever the hole is there in a plate, so around the hole the stress is concentrated more, you can observe here. Now if you want to reduce the stress concentration near this hole, so what you can do, you can drill additional small 2 holes beside like this. Now you can observe the stress pattern over this hole. In the second model, there is some less stress concentrated near this hole. So this you can achieve by drilling additional 2 small holes in this model, something like this. Now I can decide among these 2 model which is my preferred design. So this is bad design, this is our preferred design. Why? Because around this hole I made some arrangement in this model in such a way that by drilling an additional small 2 holes around this hole, the stress concentration is reducing. So that is why among these 2, this is our preferred design. Okay. So this is the first method of reducing stress concentration, by drilling additional 2 holes. Clear? So moving to a second method, that is by using fillets instead of shoulders. Okay. Here you see there is a sudden change in cross section in this model, and you can observe here there is a sharp edge in this model. So because of this sharp edge, the stress lines, the stress is concentrated more towards this sharp edge. Now how to reduce this stress concentration? So instead of this sharp edge, I am giving a fillet around this region, something like this. Now when you give a fillet, the stress concentration is decreasing. Now this is my preferred design and this is bad design. I hope it is clear. By using fillets instead of shoulders or instead of sharp edges. So by making a fillets, you are reducing stress concentration in the sharp edges region. So this is a second method. Now the third method, that is removal of unwanted material. Okay, so there is a V notch here in this first model, and as it is clear from the definition of stress concentration, again this notch is a discontinuity in a particular model. So wherever the discontinuity, that is V notch, is there, so stress is concentrated more near that region because of minimum cross-sectional area. Okay, and how that minimum cross-sectional area, so we have took one small example also in the previous lecture. Now coming to here, because of this V notch, so around this region stress is concentrated more. Now if I want to reduce the stress concentration in this, so what is the third method? Removal of unwanted material. You can see here this much material has been removed. If you remove this V notch region, that is this material, if you remove, you can observe the stress lines. There is no concentration. The stress concentration is automatically reduced. Depending on application, you can go for removing unwanted material. Okay, you can just observe by removing unwanted material using any machining method how you can reduce a stress concentration in particular model. So in this case, this is preferred design and this is bad design. I hope it is clear. Now the fourth method, that is use of multiple notches. Use of multiple notches. Okay, so in this case there is a one groove or one notch is there. Here the multiple notches have been used. You can observe here and compare both the models. Here how stress concentration is there, and there how the stress pattern is there, you can observe. So by using multiple notches, additional notches, you can reduce the stress concentration near this notch. You can compare here. So this is your preferred design, this is your bad design. We usually don't go for this if you are going for a proper design. Okay, so this is the fourth method, use of multiple notches. Now the fifth method, using larger diameter threaded length. So this is your one design and this is second design. Okay, so you just compare this model and this model. Now here it is similar to your second type of modeling. Here, from here the sharp edges will start. So around this the stress concentration is more. You can see the stress lines here, right? So instead of this, what I am doing here, you see here, larger diameter threaded length. I am using larger diameter threaded length. So if I use this one, now you observe the stress lines, stress patterns, right? So sudden sharp edge I am avoiding here. So by using larger diameter threaded length, I am reducing stress concentration. So it is easily visible from both the diagrams. So in this case, this is my preferred design, this is bad design. Okay, so usually in theory part of stress concentration, this most probably they will ask along with the definition of stress concentration, along with stress concentration factor, that is KT, which you have seen in previous lecture. So this is also very important. Methods of reducing stress concentration, if they ask, you have to draw these diagrams and mention these methods. Drilling additional holes by using fillets instead of shoulders, removal of unwanted material, and by use of multiple notches, and by using larger diameter threaded length. mention these methods and also draw the diagrams neatly. So that's it. This is the theory part. Methods of reducing stress concentration. Okay. Okay. So we are starting the problems on stress concentration. The problem number 1. Determine the maximum stress in the following cases. So we are taking case number 1. So after this we'll go for case number 2. Following cases, taking stress concentration into account. So what is in that first case? A rectangular plate of 50 mm into 80 mm with a hole of 10 mm diameter in the center is loaded in axial tension of 10 kN and thickness of the plate is 10 mm. So this is the data given for a particular problem. So by this given data, first we'll write down the given data. So given data, force, tensile force F equal to 10 into 10 raised to 3 Newton, and what is the diameter of a hole? Small d, 10 mm, and thickness of a plate H is equal to 10 mm and width of a plate small w equal to 50 mm. Correct? So we'll draw the diagram now by reading this question. A rectangular plate of 50 mm into 80 mm. So first I will draw a rectangular plate. So don't worry about this small d, h and w. So how these symbols are coming, so that also I will tell now. So this is the rectangular plate of what is the length of this plate? 80 mm. Yes, it is acted upon by a 10 kN tensile load. Yes, 10 kN tensile load, and this is a plate with a hole of 10 mm diameter. So hole is there, and the diameter of this hole, how much? It is small d equal to 10 mm. Correct? Now what is this 50? 50 is the width. Now you have to understand this plate is having 3 dimensions, right? Something like this will be there. So that 3-dimensional I will not be showing, but that section I will be showing. What is that 50? Yes. So this is now 50 width. Correct? Now what is this thickness of plate given? Which is 10 mm. This is 50 mm and 10 mm. Clear? And also the hole will be there. Now if you take a section at the hole, how does it look? Something like this, right? So this is your 10 now. So similar kind of problems you already solved in previous lecture. We took one example, right? Now this is your cross-sectional area. Now when you take a section at the hole, this is your cross-sectional area. Why you are taking this cross-sectional area only? Why you are not taking over here or here? Because you are designing for critical section. And from the previous lecture, what is critical section? That is minimum cross-sectional area. Because minimum cross-sectional area leads to higher stress concentration. So that is where the model will fail first. So that is why you are taking minimum cross-sectional area. Okay, I hope it is clear. So rectangular plate acted upon a tensile load. The whole plate, this is a plate with a hole model. A hole diameter small d equal to 10 mm. This is the width of the plate, 50 mm. And this is the thickness of the plate. Okay. Now this is denoted by small w, that is 50 mm, and this is the thickness of the plate denoted by small h. These all small w, small h, small d, and are denoting by these terms because these have been given in data handbook. In this lecture, I will be showing the data handbook, so how these symbols are coming. Okay. So this is the figure you have to draw by reading this statement, right? Now what they are asking, determine maximum stress, right? Now from the previous lecture, we know that what is stress concentration factor? Stress concentration factor Kt is given by maximum stress upon nominal stress, right? This maximum stress they are asking in this particular problem. So if you find stress concentration factor, if you find a nominal stress, you can easily get a maximum stress value. First we'll try to find a nominal stress for this. Okay, so nominal stress or theoretical stress is given by force upon cross-sectional area. What is the force here? So 10 into 10 raised to 3. So this is a force divided by cross-sectional area. You already know now cross-sectional area is this hatched portion which I am showing. What is that? 50 minus 10 into this thickness. Now solve this. 40 to 10, so this, so again 1000 by it is 40, so 25 megapascal. So you got now one data, nominal stress you have got, correct? Now you're supposed to find now Kt value, right? Now to find the Kt value, you are supposed to refer page number 46. Go to page number 46 in Design Data Handbook. In that you have to refer figure 3.17. Everyone go to page number 46. This H.G. Patil data handbook we are using. So in that data handbook, all of you go to page number 46. This is the page number 46, figure 3.7. This figure may not be visible properly in the video, but you can go to your data handbook, page number 46, figure 3.7. Now whatever this figure you are drawing from the given question, this figure you have to compare in the data handbook. This is what our problem type, exactly same problem type is there. By reading the question from the data handbook, you should be able to identify which figure you have to refer. So we are going to refer figure 3.17, page number 46. When you look at that model and this model, you can write the width W as 50. So that's how I wrote W equal to 50. Again, thickness of that plate, that is 10 mm, and diameter of small hole is denoted by small d. Okay, so that's how I am writing these symbols. Comparing our given problem with this data handbook, I am writing these values. Okay, so everyone must be having data handbook. Refer this figure so you can easily write down. What is the use of this figure? We are referring this figure to find out stress concentration factor KT. Right? Now how to refer? So you look at this figure now. Along x-axis you have small d by W ratio. First we'll write that. Okay. So small d by W ratio. So what is small d? That is 10. Thickness of plate is 50. How much you got? 0.2. Right? Now go to that figure again. So where your 0.2 lies somewhere here. So wherever this 0.2 line meets this curve, that corresponding value on y-axis is your KT value. Everyone look at the data handbook. So looking at that, I got approximate KT as 2.5. I hope all of you will get this 2.5. So depending on your accuracy, slight variation will be there, but you should get exactly 2.5. Okay. Now once again I will tell this graph by writing in the board. So this kind of graph is there on page number 46 for this particular problem type. Along x-axis d by W ratio is there. This curve is there. So somewhere here our value 0.2 is there. This line, wherever it coincides, corresponding value on y-axis, that is your KT. So this is 2.5 you are getting. Clear? Okay. Now you know KT value. This KT value you have got now, and you already know nominal stress. Simply multiply 25 into 2.5 by this relation. What is the maximum stress you will get? Calculate. So maximum stress I will get as 2.5 into 25, that is as 62.5 MPa. So this is my answer. So very simple problems. If you have attended a previous lecture, that was about 45 minutes lecture. So that is clear, then this is very easy. First write this relation, nominal stress first you find, then using graph you find KT. So multiply these two, you will get maximum stress. Okay. So this is the case number 1. I hope you have understood this. So now we will move to case number 2. Okay. So we'll go to case number 2, similar to previous problem. Determine the maximum stress in the following case, taking stress concentration into account. So this is, in that only, this is case number 2, as if it is problem number 2 only. A circular shaft of 45 mm diameter stepped down to 30 mm diameter, having a fillet radius of 6 mm subjected to a bending moment of 150 mm. So in the previous problem that was a simple tension problem. This is bending moment problem. Okay. Now by looking at the given data, first we will try to draw the diagram first. So this is a shaft of 45 mm diameter. Now this has been stepped down to 30 mm with the fillet radius. This is your fillet now, stepped down to a new diameter. How much is that? Sorry. So this is 30, correct? And this fillet radius is how much? That is 6 mm. And this acted upon by a bending moment. Okay, a bending moment F. Bending moment M, that is 150 Newton meter. 150 Newton meter. This first you will draw now. And this you are going to search in the data handbook. In data handbook, which figure will give exactly our problem type. Okay. So now you go to page number 41 in data handbook, page number 41. So it may not be visible here, but you go to your design data handbook, page number 41, figure 3.6. Observe there, our given problem type is exactly this one. A stepped down shaft acted upon by a bending moment M. So comparing our given problem with this one. Now this is your capital D. You can see in data handbook capital D. This is small d. This is a fillet radius small r. So if you have data handbook, so you can easily write down. Okay. Okay, I shall write the given data now. Bending moment M we have already written. Capital D is equal to 45 mm and small d equal to 30 mm. And fillet radius R equal to 6 mm. Okay. So which I'll write that page number. You refer page number 41 design data handbook, figure 3.6. So we are supposed to use this figure, so we'll see in today's lecture only. So before that, we are supposed to find a maximum stress. Again, stress concentration factor Kt is given by maximum stress upon nominal stress. Okay. So the meaning of this, how this will come, we have seen in detail in previous class. Okay. Now this maximum stress they are asking. So similar to previous problem, first we will find nominal, then we will find Kt. Now nominal stress is given by, here it is not force by area, it is not a simple tension problem, it is bending moment problem. Now which equation to use, I have given you in detail in previous lecture. If it is a simple tension type, what is the expression? If it is a bending, what is the expression? If it is a torsion type, what is the expression? That also I have given you. So it is nominal stress, it is a bending problem, so M by Z. Okay. And what is Z? You already know Z is a section modulus, which is also given by I by Y. You already studied in MOM, and some previous problems also you have used it, right? So either you solve by taking this, or directly, if it is simple cross section, directly you can write expression for Z. Okay. Now nominal equal to, what is the moment given? 150. How much it is? Newton meter it is, but dimensions have been given in mm, right? So 150 into 10 raised to 3. So I will write this in mm. So moment 150 into 10 raised to 3 Newton mm divided by, now very important, it is a circular cross section will be there because the diameter is given, right? What is the Z for that? Yes, if you don't know what is the I, moment of inertia for a circular cross section, if this is the diameter D, I is pi by 4, pi by 64 d raised to 4, and Y is d by 2. Now Z, what is the Z value? Pi by 32 d cube. So I'll write here pi by 32 d cube. Now very important. But here what is the diameter? Whether you are taking a small, this d value or this d value? Yes, answer. You are taking small d value 30. Why? Remember, you are designing for a critical section. Critical section means minimum cross-sectional area. So this is your critical section now, where the fillet is there. But that fillet is common to this also, this also. But minimum cross-sectional area you will get when you take this 30 as a diameter, not this 45. I hope it is clear. That is why I am taking this D as 30, not 45, because we are designing for a critical section, that is minimum cross-sectional area. Correct? So now we'll solve this. So you also solve simultaneously. So just check how much you'll get. So confirm it, 56.58 MPa. So this is your stress. So this is your nominal stress, what you are getting. Okay. So now we will try to find stress concentration, Kt. To find Kt, stress concentration, go to page 41, figure 3.6. Now in that, along horizontal you have small r by d ratio. Small r by d ratio, what is that? Fillet radius 6, small d is 30. So how much is that? 0.2. And these curves, that is capital D by small d. All of you check in your data handbook, page number 41, figure 3.6. So this capital D by small d. So 45 by 30. So how much is that? 1.5. Now you have 1.5 line. in this data handbook approximately. Yeah, so this is your 1.5 line, and along the horizontal axis you have small r by d ratio 0.2. So wherever that line coincides with this curve, corresponding value on y-axis is your kt value. So you can easily identify in data handbook. I repeat, small r by d ratio is 0.2 and capital D by small d is 1.5. Wherever those two meets, corresponding value on a y-axis, so that is your kt value. So kt I am getting as 1.4. Everyone check. So once you know kt value and once you know nominal, what is the maximum stress? Simply multiply nominal with kt. So how much you will be getting? So 1.4 into 56.58. How much? 1.4 56.58 into 0.4. So 79.212 ampere. So this is your answer. Okay. So students, if you have designed a data handbook and if you attend class regularly, especially the previous class of the stress concentration, this will be very easy. So depending on problem type, which expression you are supposed to apply for nominal stress, if you identify, it is very easy. And these things are basics of strength of materials, so there is not much difficulty in this. Okay, so go through the data handbook, so go through this figure. It's very easy to identify. Okay, so that's it for today's class. So again in the next class we'll solve 3 more problems. Okay, thank you.